probability. Today we're going to talk about calculating probability, addition rules, and complement rule. There'll be a few other topics, but those are the big ones. Okay. Before we get started, I just want to remind you of something we talked about before, which is what is a discrete probability? So, here's the formal outcome. And basically, a discrete probability has a finite number of outcomes, whereas a continuous random variable has an interval of outcomes, like what temperature is it? And we could say like it's 29.65. Whereas a discrete random variable would be like, how many pets do you have? And you'd say 1, 2, or 3, and it's typically a whole number. Okay, so for this lecture, we're going to mainly focus on discrete probabilities. Okay, and just how do you calculate a probability? Well, there are two ways. There's this theoretical way, which is the number of ways the event occurs divided by the total number of outcomes. And there's numerically with data, which is more common. And it's the number of times the event occurs divided by the total number of observation. Okay, when the total number of observations can be thought of as the sample size. Okay, well, here's a little example. And this is a real data set in which we have smoking and lung cancer. And there are 86 lung cancer patients, 86 controls. So 86 with lung cancer, 86 without. So the probability of lung cancer here is artificial. It's 50% because we have an equal number of observations in each category, and that is due to the research design. Okay. The goals of this paper were to see whether the odds of lung cancer are greater for smokers versus non-smokers. But we're going to do some side calculations to demonstrate a few things about probability. This is the data set here. It's count data, so hence it has a finite number of outcomes because we're just counting things, and it's discrete. Okay. If you want to look up this data set, you're more than welcome. There's two sources right there. So just to get started, obviously we're using an observational data set, so our method of calculating probabilities is going to be this one. Number of times the event occurs divided by the total number of observations. Okay, so let's do a few calculations. Okay, the total number of observations, we just added all the cells up, all the counts of the cells, and we get 172. Now, if we look at an individual cell, such as smoking and cancer, that would be this 83. And if we want the probability of being a smoker and having cancer, it's this observation count, 83, divided by the total sample size, 172, and we get 48%. Okay. Probability of non-smoker and cancer, well, that's 1.74%. So, just a few calculations there. The probability of a smoker is going to be 83 plus 72, which is 90% probability of cancer, and I'll go through that calculation of smoker. So if I want to determine how many smokers there are, it's going to be those that smoke and have cancer, and those that smoke and do not have cancer. So we have to add the 83 plus the 72 together because there's more than one type of smoker here. So please keep that in mind and be careful about that. Okay. So we add those two together, we get 90%. The probability of cancer, well, again, we have to go back. So we go to this cancer column. It's 83 with that are smokers and have cancer, and 3 that are non-smokers and have cancer. Okay. So we just have to add the 83 and the 3 together, and we get 50%. Okay. Now, if I want to talk about the proportion of individuals who have lung cancers who are smokers, well, this is kind of sneaking in some material that is not required. And here, the important thing to consider is that I'm restricting this population to those who have lung cancer, but also who are smokers. So the restriction is that you have to be a smoker. Okay, so the smokers, they're 83 with cancer, 72 without. Okay, so that should explain our denominator, 83 plus 72. And I want only those who have lung cancer. There's 83 of them. So it's 83 divided by this number. That's 53.5. I could also ask us to restrict our population to those who are not smokers. So I have to go back to this data table. Non-smokers is 3 plus 14. Okay. And of the non-smokers, 3 have cancer, 14 do not. Okay. So there are 3 here because there are 3 without lung cancer, but I'm restricting to the population of not smokers. So it's just that single 3, and that's 17.6%. So you don't have to worry about that too much. I just want to show, that you can ask different probabilities. I'm not going to emphasize that. Okay. Now, while we have these probabilities up, I just want to illustrate this thing called the general addition rule, and it's going to be very important for you. Okay, if I was to ask what is the probability of being a smoker or having a cancer, I could just count them up, right? Let's go back to the data. Smoking or cancer, I can take 3 who are non-smokers and have cancer. I could take the 83 that are smokers and have cancer. Or I can take the 72 who are smokers but don't have cancer. And when I go ahead and do that, I get all of this. And I divide by the total sample size. There's no restriction on population. And 91.8% of the individuals in the study are either smokers or individuals with cancer. Okay. Now I want to illustrate this calculation in another way. Okay. And that is, I could take this probability of smoking, which is a probability of cancer, which is this 83 plus 72, we saw that on the last slide, divided by the total sample size, that gives me probability of cancer, plus the probability of being a smoker, that's 83 plus 3. But you'll notice I've counted these 83 individuals twice, so I'm going to subtract once by it. And that's subtracting by the probability of being a smoker and having cancer. This general rule right here, to see that I can work out this probability in 2 ways, that's called the general addition rule, and it's summarized in this form and bolded right below. Okay. Well, the complementary event of an outcome are all the outcomes that make A false. So if I have an outcome A, I want to find all the ways that make A false. That is the complement. And it's denoted by A. It commonly has a superscript of a C. The complement rule just says the probability of A is 1 minus the probability of A complement. And we can see this right away. Probability of smoker is 90.11%. Okay, but I could also take 1 minus the probability of a non-smoker, and when I add up all the non-smokers, there's 17 out of 172 of them. That's again 90.11%. Okay. Now, some calculations of probability are made easier by the complement rule, and some of them are much harder. So for example, if I want to calculate the probability of a non-smoker or no cancer, I would need to track down all three of these events. So the number of ways this could be satisfied is I could be a smoker and not have cancer, I could be a non-smoker and have cancer, or I could be a non-smoker and have no cancer. It'd be easier if I just took the complement of this event. 1 minus the probability of smoker and cancer. That's a single calculation. It makes this much quicker. Okay, so sometimes knowing these rules is going to be useful and save you a lot of time. Okay. Now, going back to the data set and its original purpose, we want to see how much more likely someone is to have cancer than not cancer. And the right way that this paper captured it was with the odds. And that's not in your textbook or anything. But here are the odds of cancer. And keep in mind, odds doesn't have to be a number less than 1. Like you could have odds of 2 to 1, or 3 to 1, or 10 to 1. Okay, so odds and probability aren't the same thing. And yeah, at least right here, and keep that in mind that odds is kind of an odd word, and you need to be careful of the odd ones. Okay, the odds of cancer here is just the ratio. So we're going to look at, for smokers, so we're going to go back to this data set. A smoker, there's 83 smokers, and we want to know the odds of cancer, but only for the population of smokers. So I'm only going to look at this side of the data, that row. There's 83, so the odds if you are in this population is 83 divided by 72. The odds if you're in the non-smoker is 3 divided by 14. And we're going to compare those two. Okay, so 83 over 72, that gives me a 1.15 chance of cancer if you're a smoker. And we need a baseline here. What do we want to compare this to? So this odds ratio is for comparing two populations. I want to compare that to people who don't smoke, because like 1.15 doesn't sound that bad, but I need a baseline. Here the baseline I need to pay attention to is, well, what would your odds be if you weren't smoking? Okay, and for non-smokers, there are only 3 individuals who have cancer out of 14. Okay, for whatever reason, they got cancer, but they are non-smokers. And it's a 0.21 odds. It's much, much smaller. To capture this difference, how much worse are your odds? We take the ratio. So 1.15 divided by 0.21 gives us a 5.47 odds ratio. And that indicates the odds of having cancer for the smoking group is 5.47 times greater than for non-smoking individuals. Okay. Now I just want to bring back like the sampling method that was used to collect this data. And in conclusion, there is strong evidence that the risk of lung cancer is greater for smokers rather than non-smokers. But that we should also acknowledge that this is a retrospective observational study. Is smoking causes lung cancer? That cannot be addressed by the statistical analysis because we don't have a designed experiment. The inference that you make from this data to the wider population is only appropriate to the extent that the samples of cancer patients and controls constitutes a random sample of the population with and without cancer. Now that is a load of statistical jargon right there. And basically it means that To the extent that you believe that this data represents the population and is a random sample of it, you can make your inferences. Okay. Now let's move on to another example here. So here we have a certain population that has a disease A and 15% of the population has disease B. We also know that 5% of the population happens to have both disease A and B. Now my question here is, what's the probability a randomly selected person in this population has disease A or B? Well, this is a perfect example to use the general addition rule. So probability of A or B equals P of A plus P of B minus P of A and B. And we get 20%. So 10 plus 15 minus 5 gives us our 20%. Okay. I can ask a follow-up question, such as what proportion of the population has disease B and does not have disease A? Okay, so disease B alone minus those with disease A, well, I know that there's 15% with disease B, and of those with disease B, 5% also have A. So I just do the subtraction, I get 10%. Okay, and if I want to logically or mathematically break this down, this is what I'm using right here. Okay, I can use the complement rule here to answer this question. What's the probability someone doesn't have disease A? Well, it's 1 minus P of A, or 1 minus 10%. I get 90% there. Okay, I gave an observational probability example. How about I give you an example of a theoretical probability? So I'm going to consider the example where I toss 2 coins, and the sample space is the set of all possible outcomes. Well, every single outcome here is the set of all possible outcomes. I just wrote it down. This thing is the sample space. So coin 1, this HH indicates that coin 1 landed heads and coin 2 landed heads. This tails head indicates that coin 1 landed tails and coin 2 landed heads. So TH is put there. Likewise, we have head tails and tails tails. Okay, so this is our sample space. Let's ask a few more questions. So I have an event A that's any subset of the sample space, and I can ask probabilities about A. I can also ask about the complement of A, which is the set of all events in S that are not in A. I can ask for intersections between 2 sets. If I have any other subset of the sample space B, the intersection with A with B are the set of events that are in both A and B. And this is called an AND probability. The union of A with B is the set of events that are in A or B, and this is an OR probability. Let's do a few examples with this coin tossing. So A is the event there exactly 1 head in 2 tosses of the coin. So that is when you toss 2 coins. B is the event that the first coin lands heads. So A, there is exactly 1 head, so that could be heads, tails, or tails, heads. A complement, the thing that makes that false, is there are no heads. So it would be tails, tails, or heads, heads. Okay. Now B is the event the first coin lands heads, so its outcomes are heads, tails, or heads, heads. And its complement, while not listed here, would be tails, heads, and tails, tails. Just FYI. Now A and B, that's the intersection of A with B. Well, what event do they share in common? Is this heads, tails? So that's A and B. A or B is all the events in A or B, so I just write down the event A, then I say, oh, I already listed heads, tails, so I just have to list heads, heads, and this is it as a set. Okay. Now, if I want to calculate probabilities, I just have to count number of events. A has 2 events, that's 2 out of 4 possible outcomes. Remember, the sample space has 4 outcomes. Okay, so 2 out of 4. Probability B is 2 out of 4. A complement has 2 events, and I could calculate directly as 2 fourths, or I can use the complement rule of 1 minus 2 fourths. Probability of A and B, there's only one event they have in common, so it's probability of 1/4. Probability of A or B, there are 3 events, so it has a 3/4 probability, or I can use the complement rule, which is given right there. And again, I get 3/4. Okay. This kind of theoretical probability is used a lot. Okay, and I just want to talk about this dude called Mendel, who was a monk and very, very interested in botany. He studied both botany and mathematics at the University of Vienna and was a science teacher. But he also grew peas, okay? And he carefully pollinated plants, saved the seeds to plant separately, and analyzed the data in succeeding generations, okay? He self-pollinated plants until they bred true, giving rise to similar characteristics generation after generation, and he studied easily distinguishable characteristics like color and texture of the peas, color of the pea pods and flowering, and the height of the plants. Okay, when he crossed true breeding lines with each other, he noticed that the generations of the offspring consistently showed a 3-to-1 ratio in the second generation. So just a few things. When you're crossing a plant, there's going to be what you can consider a mother and a father, so pairs. And he's going to be looking at the characteristics of the mother and the father. And these characteristics could be color, texture, and wrinkled or non-wrinkled of the pea pods. Okay, and we'll see that data in a minute. Okay. So if we look at seed color, Mendel showed a true breeding yellow pea and a true breeding green pea were crossbred. So if they were crossbred, their offspring produced a yellow seeds. But in the next generation, the green peas appeared at a ratio of 1 green to 3 yellow. And this phenomenon Mendel coined the recessive and dominant. Okay, so this was more or less the explanation for recessive and dominant genes that we know today. So in the preceding example, the green trait, which seems to have vanished in the first familial generation, is recessive and the yellow is dominant. He eventually published his work, and these invisible factors are what we call genes today. Okay, so let's look at this crossing. Okay, so these are gametes from heterozygous parent crossed with, so you could consider, this to be mother or father, and this to be the opposite. So if the top is like the father, the side here will be the mother. So these are gametes from heterozygous parent, and they have these characteristics. Yellow round crossed with yellow round produces YYRR. So that is our yellow round, dominant, and here dominant yellow, dominant R, and so this is the parent generation here, and the F1 generation is produced right here. Okay, here is our F2 generation. So we have a yellow round crossed with yellow round. Again, we get YYRR. There are some capitals there except for the last R. But here, if we cross YR with lowercase capital YR, yellow round, with recessive YR, we're going to get a dominant yellow, a recessive yellow, and a recessive round round, and this is going to be a wrinkled yellow Peapod. Okay, and we see that we can get this wrinkled characteristic in 4 ways. Okay, one of which produces a green one. Okay, and so this has probability of being wrinkled is 4 out of the total possible outcomes, which is 16 here. And so there are certain probabilities when you, with each generation of Peapod. Okay, so let's work these out. So what is the probability of a green offspring? Well, let's count the number of green. There's 1, 2, 3, 4. 4 ways to get a green out of 16, 1/4. What is the probability a Peapod crossed at random is wrinkled? We just talked about that. There's 4 ways, 3 of which are yellow, 1 of which is green, and that's 4/16 or 1/4. What is the probability a Peapod crossed at random is green and wrinkled? Well, there's only one way to get that in the bottom right here, so it's 1/16. Okay, and what Mendel did is he collected data that also backed up these probabilities. Okay, so now we can also talk about what is the probability a Peapod crossed at random is green or wrinkled. Well, probability green is 4/16, probability wrinkled 4/16, minus green and wrinkled, because this is the general addition rule, will be minus 1/16. That'll give us 7/16 probability. Okay, probability a Peapod crossed at random is not wrinkled is 1 minus the probability of wrinkled, and that's 3/4. Okay, so just a couple of rules of probabilities illustrated there. And now I just want to show for you a couple of rules that every probability density function must satisfy. Okay, now to make sense when we talk about probability, the sum of all probabilities has to be 100% when they're distinct events. Okay, so that means you're not counting probabilities twice. Each probability has to be, greater than 0, greater than or equal to 0, and less than or equal to 1. Okay, so we can't have negative probability, we can't have probability that's greater than 100%. So just some common sense things for probability. And we can use this. So here's a probability density table right here. But we don't know what the probability of x equals 1 is. So we're just going to use this property. The total probability has to be 1. So I just add these up. So this P of x equals 1 plus 0.3 plus 0.4. I just solve for P of x equals 1, and I see that it has to be 0.3. Okay, so that is our probability right there. And that completes my podcast on probability. Thank you.